In this video, we are going to apply the rotational energy bucket model to this problem where we have a hanging mass that has a rope that goes over a pulley and which is attached to a spherical shell. And what we want to do is we want to find out after this mass has fallen a certain distance here, y, right here, after it's fallen distance y, how fast is it going? What's its linear velocity? So we can analyze this from an energy point of view. So let's do step one, reference line. I'm going to use the falling mass as the object of interest, and I'm going to say the reference line when it gets to this point down here. I want to say that's the reference line. And step two, I'm going to clearly identify A and B. Energy point A equals energy point B. So I'm going to say A is right here when it first starts moving, and B is right before it hits the ground down there. That's point B. Okay. Step three, we are going to apply our rotational energy buckets to this problem. So here's our kinetic bucket with our translational and rotational ink cartridges, and then we have gravitational potential energy here and spring. So we have kinetic UG and US. Over here we have, on this side, we have translational and rotational energies, possibly gravitational and spring energy here. Kinetic, UG, and U spring. Okay, so if this object starts from rest and nothing's moving, there's no kinetic, we do have potential because the little mass m is above the reference line. No spring. Now at point B, we do have translational because the object is falling down and we have a linear velocity. And then these two are also spinning, so we have rotational. So we have both these. We have actually two rotationals. No more gravitational and no spring. Okay, so the resulting equation becomes, let's see, this is mg y, that's the distance y there, equals, let's see, the translational kinetic energy of the falling mass is 1/2 mv squared. The pulley, I'll go in this direction here, the pulley's rotational inertia is 1/2 I pulley omega pulley squared plus 1/2 I the spherical shell omega shell squared. Okay, so that's our energy equation. Translational for the falling object, and then this is the pulley, and this is the sphere. Okay, so here's our linear velocity, except that we have these omegas in here, which are rotational velocities. They're related to the linear, but we want to somehow get those out of there. So the key point is that when things are, all linear quantities are the same. So if I put a person right here on the rope right here, that person is going to travel at linear velocity. And if they're a person on the rope over here, let's say, hanging off here, that person will be traveling the same linear velocity as that guy. So linear quantities are the same. So what I can say is V is equal to omega R. So really omega is equal to the linear over the radius. That's how we can relate the linears and rotationals together. So I'm going to get rid of the omegas and make them all V over R's. So if I rewrite this, I get 1/2 mv squared, the linear, plus 1/2. I have the pulley. This is going to be V over R pulley squared, right from there, V over R, plus 1/2. I have the spherical shell, V over R spherical shell quantity squared. So you can see here I have a V squared term, V squared term, V squared term, V squared term, which is good. So I'm going to factor that guy out. So I'm going to get V squared is equal to, or excuse me, not equal to, it's going to be times V squared times a 1/2 m plus a 1/2. Now a pulley is usually a disc, so I'm going to say this is a 1/2 mass of the pulley R of the pulley squared. Okay, so this is going to be 1/2 mass of pulley r of pulley squared divided by r pulley squared for that one right there. So those actually go away. And then 1/2. Now this is a spherical shell, so it's hollow inside. So a spherical shell, not a solid sphere like a bowling ball. A solid shell, or excuse me, a spherical shell is 2/3 m r squared. Okay, so this is going to be 1/2 2/3 mass of the shell r of the shell squared divided by this one over here, that r shell squared, so those go away. And in fact, that 2 goes away right there. So my final answer, if this is an mgy over here, the final answer is going to look like v is equal to, so I've got that mgy on the top, divided by each of those terms, the 1/2 m, this one over here is looks like a 1/4 m pulley, plus this looks like a 1/3 mass of sphere, and that's all square root. So that's our final answer right here. We have the square root of mgy over the total mass. Basically, it's the total mass of that entire system. Okay. So in retrospect, we used the rotational energy buckets. We have an equation where we're going to have linear velocities and angular velocities. However, with this relationship right here, and knowing that linear velocities are the same for everybody, I can eliminate omegas and put in velocities. Then I can solve for linear. And then if I need to solve for omega, I can always go back and multiply by r, because all these two things have different r's, so you can have different rotational velocities. So that's how we can apply the rotational energy bucket model to this problem.